Hey class, Adam Ward here. First lecture today on open channel flow. This will be the first of a series of 3 lectures that we'll do. And the idea today is just going to be to introduce us to some basic concepts that we'll see in open channel flow. So there are 3 lecture recordings that go with today's content. When you get through those 3 lecture recordings, here are the learning objectives. This is what you ought to be able to do by the time you get through today's material. So I want to start open channel flow by thinking about how we describe flows. And so one way that we describe flow that you're already familiar with is Reynolds number. Reynolds number we've defined was density times velocity times a representative length scale, d for pipe diameter, for example, divided by fluid viscosity. And we used Reynolds number to differentiate 2 types of flow, laminar flow versus turbulent flow. And those had very different characteristics in the way that they move, the way they interact with the environment, and the quantitative predictions that we use. Similarly, for open channel flows, we have another dimensionless term called the Froude number. And you all are plenty capable at this point in the semester of doing the dimensional analysis and actually deriving a Froude number yourself. So Froude number looks like this. Fluid velocity v divided by the square root of gravitational acceleration g multiplied by y, which is the depth of flow in an open channel. So what Froude number is telling you is a ratio. In the numerator is how fast does water move. And this term in the denominator, this square root of g times y, this is what's called wave celerity, or shallow wave celerity. And this is actually describing the speed that an energy wave moves in shallow, still water. And so the way you might visualize this in your mind is picture that there's a still pond and you throw a rock in it and you create ripples. The speed that those ripples move is the square root of gravity times the depth of water. So Froude number is telling you how fast does the water itself move relative to how fast energy waves propagate through that system. So if the water particles themselves are moving faster, that means the numerator is the larger value. You get a Froude number greater than 1. If the energy waves are traveling faster, you get a Froude number of less than 1. That would mean that the denominator is larger. So there are 4 cases that we're going to look at with the Froude number. So the first case, we want to think about velocity equal to 0. So this is the simple case that I just described on the previous slide. If we throw a rock, shown in black, into a still pond, the ripples that are formed would move equally in all directions. And the speed that they would do so would be that shallow wave celerity, square root of gravity times depth. Now, in the second case, we're going to consider a slow-moving water velocity. So a Froude number, the velocity would be smaller than the denominator, and so this would be a Froude number less than 1. Sorry, had that miswritten. Froude number less than 1. And so consider in this case that we've got a river, and that river is moving slowly from left to right on the screen, and we throw that same rock in. So what's going to happen will depend on which direction we're looking. So in the downstream direction, shown in orange, the ripples that are going to move at the speed of water. So they're all being advected from left to right, just like a conveyor belt. So the river itself is going to contribute to how fast they move, and they'll propagate downstream at the square root of gravity times depth. In the upstream direction, ripples can still move upstream. And so in that case, even though the velocity of water is moving one way, the ripples are faster. So the ripples can actually move in the upstream direction. That won't be nearly as fast as they move in the downstream direction. But if you throw a rock into a river with a Froude number of less than 1, you'll see ripples go both ways. If you look down on it from the surface, it'll look sort of like an ellipse. It'll be stretched out in the downstream direction. So it's this asymmetrical shape that you get. Now, importantly here, what this means is something that happens downstream, like the rock, actually has the ability to control what's upstream of it. So the upstream flow responds to these downstream perturbations. And we call this subcritical flow. So Froude number less than 1 is our key indicator of subcritical flow. Velocity is less than, yeah, okay. Third case, what if Froude number is equal to 1? We've got a velocity equal to that wave celerity. We call that critical flow. And again, if we think about throwing a rock into a moving river here, so we've got our river with some velocity of water moving from left to right. The downstream wave will do just like it did before, but in the upstream direction, you'll get something that we call a standing wave. And this occurs because the wave is able to propagate upstream at the exact same velocity that the water is moving downstream. Right? You might think about this like if you were on an escalator or one of those moving walkways, right? If it's moving one direction and you start walking the wrong way on it, you are a standing wave. Right? You're not moving. You don't have any net motion left to right because your energy being exerted one way is exactly opposing the velocity moving the other direction. And the final case is when the water velocity is much greater than wave celerity. And in that case, you get a Froude number greater than 1. And we call this supercritical flow. And so in this case, if we throw our rock in, and again, we've got fluid motion from right to left, so this is a moving river, the wave and the water are working together. That downstream propagation happens the same way. But there is no ability for the waves to propagate upstream. So in supercritical flow, there isn't this propagation of a downstream perturbation being able to affect what's upstream of it. In a supercritical condition, flow has no, you almost think like it has no memory. Like what happens downstream doesn't affect what happens upstream. There's no such thing as flow backing up or responding because of some downstream perturbation. So supercritical flow, the important thing for you guys to know is that downstream changes cannot propagate upstream. Now, if you're having trouble visualizing how all of this might work, there's a simple example that you can do in your kitchen sink. So turn on your faucet and put a flat dinner plate down below. And what you should get on that flat dinner plate is something that looks like what I've sketched here. So you get this sort of round area that it has very thin, fast flow, and then you'll get what looks like a little sort of turbulent, bubbly spot, and then you'll get deeper flow as you near the edges of the plate, right? And what you're actually seeing there is where that flow is incredibly fast and shallow. That's supercritical flow. Then you go through a standing wave and transition into subcritical flow on the outside of this. So take a dinner plate, set it flat on the bottom of your sink, turn on the faucet full blast on top of it, and you can form subcritical flow, critical flow, and supercritical flow right in your kitchen sink and actually take a look at what these things look like. Now, one more way to help you think about the difference between fluid flow and energy propagation. And we're going to look at an experiment that the U.S. Geological Survey did. So what you see in the top left here is a dye tracer. And so what I've circled in yellow is actually a man standing there holding a fire hose of this concentrated dye. And so what was happening in this case was just downstream of the Glen Canyon Dam was a series of pulses of flow. And these were being released to try to mimic environmental flow conditions. So they were sending sort of open the gates, close the gates, open the gates, close the gates, to send this series of waves of water down through the canyon. And the Geologic Survey took advantage of this. And so on the rising limb of that very first wave, you can see I've circled it in green and showed you where it is on the map, Lee's Ferry. And so just downstream of the dam, they did this fire hose of dye injection. And as that signal, as that dye propagated its way down through the canyon, they measured its concentration at several points. So you can see, for example, where the Little Colorado River enters, I circled in red, and Nice Canyon circled in purple. So what I want you to see here is the difference between how fast water moves and how fast energy moves through the system. So inject on the rising limb of the first wave. That green, that's propagating downstream as energy waves, right? So those are these pulses of high flow, right? Those actually propagate through the system like energy waves. And it's somewhat unintuitive, I think, to envision that water and energy don't move at the same speed through the system, right? So for energy waves, I want you to think about maybe you and a partner are holding the two ends of like a jump rope, for example, right? And you take your arm and you start to shake your arm up and down and up and down. And what you're doing is creating energy waves that propagate down the rope to the other person. But that doesn't mean the rope moved from left to right. Like, you can make an energy wave without having any net motion of the mass, right? So energy waves move at a different speed than the jump rope in that example. In the same way, in this experiment, the energy waves are about the river's ability to transmit energy downstream. The dye is the actual particles of water themselves. So how fast did the water move? And so what you can see here is that at the upstream end, the first wave and the dye are coincident with one another. As you move to that second point, the dye is not on the rising limb of the first anymore. It's been delayed in time. It's not showing up until that first trough. And by the time we get all the way to the downstream end of this, that dye is now on the third energy wave, right? And so what we're seeing here is that energy waves are propagating through the system faster than the fluid, or that wave celerity, root gy, is larger than the velocity of water. Now that tells us that we would end up with a Froude number less than 1, and we would think of this as subcritical flow. So in subcritical flow, just to drive it home one more time, the water moves more slowly than the energy waves, right? In other words, the water is slowly translating, and these energy waves cause it to get deeper and shallower, but water getting deeper and shallower doesn't cause a net movement of the water, right? It's kind of unintuitive that energy waves can propagate through the system totally independently of how fast the water itself is moving. But that's what the Froude number is all about, telling us which is faster, the motion of the dye or the motion of these flood pulses. And in this case, it's the motion of the flood pulses that wins. All right, so I will see you back momentarily. I have one more video about how we're going to think about open channel flow. We're going to introduce the concept of specific energy, and then in a third video, we'll do an example. Thanks for sticking with me all.